In this video, I'm going to discuss tolerances of profile. Now, there's two geometric characteristic symbols associated with profile: profile of a surface and profile of a line. Profile of a surface looks like a D that's been knocked over. Profile of a line looks like a rainbow. Now, the difference between them is that profile of a surface is a 3D tolerance. What that means is it controls an entire surface, whereas profile of a line only controls individual cross sections. So a good way to compare this to something we've already covered is the difference between flatness and straightness. If you recall, when you apply flatness to a surface, it controls that entire surface. You have to run your indicator left and right along the surface. With straightness, if you applied it to a flat surface, you only have to run your indicator in one direction, an individual check. So you could essentially have a corrugated part in the other direction. Profile works in a similar way. The big difference, and I'll explain more about this in a minute, is that profile is not limited to flat surfaces like flatness and things like parallelism are. Profile can be used for curved surfaces, surfaces of revolutions, and flat surfaces. So it's a very versatile geometric characteristic. Now, another thing with profile, which I'll talk about in detail in a minute, is that it can do a lot of different things. Now, profile can mean the exact same thing as flatness if it doesn't have any datum references. Profile can mean the same thing as parallelism or perpendicularity if it only has one or sometimes two datum references. Profile can control the location and size of features if it controls a feature in all 6 degrees of freedom, which normally means 3 datum references. And I'll try to give you some concrete examples of what I mean in just a minute. First, we need to talk about the profile tolerance zone. It's going to be based on the true profile. The true profile is normally dimensioned with basic dimensions. The newest version of the ASME standard, that's the only way you can do it. Older versions of the ASME standard, you can sometimes use plus or minus dimensions with profile, but that would kind of get confusing. Normally, if you've got a profile, you want it to be a basic dimension. The true profile is the theoretically exact place where the tolerance zone lies. So normally, if it's equal, bilateral equal tolerance zone, you got half your profile tolerance on one side of the true profile and half on the other. So imagine this part is defined with basic dimensions. So each of these humps would have a radius on it, which would be basic. You'd have probably the width would be basic and the height would be basic. However it got dimensioned, doesn't really matter for our purposes. Basic dimensions. The true profile is located by those basic dimensions. And when it's an equal bilateral tolerance, aka the tolerance is split on the true profile, which is the default requirement, you've got half your profile inside and outside of the true profile. What I'm trying to get to is that the true profile is normally just the part outline, so the visible lines on the drawing. And then your tolerance zone just follows the part. So the technical way to define it is that tolerance zone is perpendicular to the true profile at every point. So that just means if we choose this point right here, we draw a line through it, it's perpendicular, right? We could do the same thing here, same thing here. It's much easier down here. Right? The length of each of these lines is 20 thousandths. 10 thousandths of the line is on the inside, 10 thousandths on the outside. And then we can just draw our tolerance zone around the true profile or part outline. Now, if you don't stick around for the rest of the video, just know that if you have a unilateral or an unequal bilateral tolerance, this isn't quite true because your tolerance zone can get shifted one way or the other, and I'll go through that in just a second. Now, What profile is saying is that the surface of the part must lie between these two tolerance zones. Pretty straightforward, right? For a flat surface, it's a fairly straightforward check. You know, you would check this the same as flatness. Now, up here with this curved surface, that's where you can get into problems. That's where a CMM machine comes in real handy, but there are ways to do it on the plate. Now, a lot of the ways are comparative, so you'd have a control part that you knew was just about perfect. You could set your indicator on the control part and then come over to your regular part and check it at individual points. Now, a bunch of different ways to do it, but what I'm trying to get across in this video are the drawing requirements. Now, if you notice, there's no datum references on here because I haven't called out any datums on the part. This would just control the form of the surface and the size of the part because there'd be basic dimensions on here. Now, let's chat a little bit about the limits of application. So a profile tolerance, according to ASME standard, is supposed to apply until there's an abrupt change in direction. That means different things to different people. So one person might say, this is an abrupt change, so this profile goes all the way down here. Another person might say, this isn't an abrupt change, it just depends. The best way to specify it on a drawing, if it's unclear, aka not a sharp corner, is to use the in-between symbol. So we identify the point we want to go to with a note and a letter, and then the other side, the point we want to go to with a note and a letter, or a leader and a letter, however you want to word it. And then under the feature control frame, we use the between symbol, which is just two arrows, and we put those two letters. So we're saying this 20 thousandths profile applies from G all the way over here to H. And then this 10 thousandths would apply on this bottom surface only. You saw me do it before. You can also use the all around symbol if you want the profile to just go around the whole part. What can happen, especially as drawings start to get revised and changed, is it can get a little confusing as to which tolerance applies where. So if you just glanced at this drawing and see this profile 10 thousandths all around, it's possible you could ignore this, even though it's going to take precedence over this. The way you avoid that is beneath this one, we're going to write except as noted to alert the reader of the drawing that there's going to be some exception to this all around symbol. So that just covers us and makes sure the reader is redirected to the other tolerance. Now this isn't limited to profile, this can be used with other tolerances as well whenever you have potentially overlapping tolerance zones, which often happens if you're using the all-around symbol. Now, the all-around symbol is two-dimensional, right? It's just controlling around. If we wanted to apply the same tolerance to the front and the back of the part, we just add a concentric circle, and that gives us an all-over tolerance. So that's a new one that came in the 2009 standard. So you can apply a profile to the entire surface of the part, which can be convenient. Now, let's get into the tolerance zone boundaries. Now, you can have a uniform tolerance, which is the most common way to do it, or a non-uniform tolerance. So you could potentially have the tolerance be wide at one side of the part and narrow at the other side of the part. Now, I'm just going to talk about uniform tolerance boundaries. I think the non-uniform is a more advanced topic. If anybody needs more information about it, I'd be glad to make a video, but for now we'll focus on the nuts and bolts of profile. So the default requirement is a bilateral equal tolerance zone. Like I mentioned before, with this 20 thousandths, you get 10 thousandths on one side and 10 thousandths on the other of the true profile as defined by the basic dimensions. That's not always what the designer wants. So often you would have two mating parts where the basic size is 1 inch. So instead of changing the nominals to make them fit, you could just say, okay, I'm cool with the line-to-line fit. I'll make one unilateral in one direction, the other unilateral in the other, and they're going to fit up no problem. The way that we do that The way we make a profile tolerance either unilateral or bilateral unequal is by using the unequally disposed symbol, which is a U with a circle around it that goes to the right of the tolerance value. On the other side of the unequally disposed symbol is going to be a value, anywhere between 0 and the full tolerance value. So in this case, it could be 0, 10 thousandths, 20, 30, or 40. Or it could be a decimal of those, but normally you wouldn't add more decimal places than is already right here. Now, this value indicates how much of the tolerance is in the direction that would add material. Now, what that means, I've got an example here. Now, just imagine this is all defined with basic dimensions. Profile, 40 thousandths, unequally disposed tolerance. 0 of that 40 thousandths is in the direction that would add material. 0 of 40 thousandths is in the direction that would add material. What would add material to a hole? Making the hole smaller. That's saying 0 is in that direction. So the entire 40 thousandths tolerance zone is inside of the true profile is indicated by basic dimensions. In this case, the hole could only get bigger. Now, from a manufacturing standpoint, you probably want to take this and then fix the basic dimension to make it in the middle of here for your tool paths, but that's a different thing. Now, in this case, for the external feature, profile, 40 thousandths, unequally disposed, 0 of that 40 thousandths is in the direction that would add material. What would add material to this square? Making the square bigger. 0 of the tolerance is in that direction, therefore the tolerance zone is totally within the true profile. So that square can only get smaller. Now what happens if we go entirely in the other direction? Profile, 40 thousandths, unequally disposed, 40 thousandths is in the direction that would add material. In this case, the tolerance zone is totally within the true profile as defined by basic dimensions which I've omitted on this figure to save some room. Same thing out here. 40 thousandths, unequally disposed, 40 thousandths is in the direction that would add material. The tolerance zone is entirely outside of the true profile as defined by basic dimensions. Now, let's get into the levels of control with profile. It depends on the datum references. It's a great way to learn GD&T because you have to pay attention to what the datum references are telling you. It gives you the level of control the profile is intended to cover. All right, so the first one, we've got a profile, 10 thousandths applied to a flat surface with a size dimension locating it. In this instance, profile does the same thing flatness does. If you recall, a flatness tolerance is two parallel planes in which the surface of the part must lie between. The profile tolerance zone is worded different, okay? It's perpendicular to the true profile at every point, but what you end up with in either case is a zone of 10 thousandths in which the surface of the part must lie. Now, this zone must lie within this larger limits of size, so this profile does not control location. The limits of size control location. Now, it would be incorrect to use a basic dimension with this because there's no datum right here. So that's using profile as flatness. The next one, we're going to use a profile of 10 thousandths to datum A. Now, what's important here is that we have a plus or minus dimension. Now, this isn't allowed per the current ASME standard. I'm putting it here to just show you how profile works. It's something you might run into. Not everybody makes every drawing per the current standard, right? So what this does, we've got a 10 thousandths tolerance zone to A. So that's essentially a parallelism call out. That tolerance zone needs to be parallel to A, but it's located with this larger plus or minus dimension. So this is essentially profile masquerading as a parallelism tolerance. Again, you really shouldn't do this. You should use a basic dimension, but when we do the right thing and use a basic dimension, if you notice, all of this tolerance went away. Now, the profile is controlling the location of that surface, as well as the size, as well as the form, and the parallelism. It makes it much more restrictive. Even though all we did was change from a plus or minus to a basic dimension, this becomes a much more restrictive tolerance. Now, we can fix that with a composite profile. We could essentially have a composite to 40 thousandths in the top segment, and then do 10 thousandths just to A, and essentially get the same thing as a plus or minus tolerance. I'll go over that in some other video. Now, profile also does something that none of the other tolerances do. It controls coplanarity. Now, in the ASME standard, it's clearly stated that even a profile with no datum references controls the coplanarity of surfaces. So what does that mean in the context? Let's look at this. We've got a flatness applied to 3 surfaces, and we've got this dimension that applies in 1, 2, 3 places. That does not control coplanarity, because flatness is an individual requirement. So is parallelism. What you could get with this part are 3 very flat surfaces that have nothing to do with each other. So you could end up with something like this, where the 2 red lines are indicating the total tolerance within the limits of size, and the individual blue lines indicate this 10 thousandths of flatness. Each surface is flat to itself. Now, this might be okay in some applications, but it's worth knowing that that's the requirements you're putting on the drawing. Now, what profile does is control the surfaces to each other. So instead of them being individual, now the tolerance zone goes the full length, and every one of these surfaces must fall within that tolerance. Now, this profile doesn't have any datums on it, so it's not related to anything, but this can be used to control the flatness of the surfaces to themselves within the limits of size like this, or it could be used like parallelism, or it could be used with a basic dimension to control the size, location, and everything else. So that's a really important thing that profile does. It controls coplanarity. So if these 3 surfaces were to serve as a datum feature, you would want to make sure they're coplanar enough so the part doesn't rock when somebody's trying to measure it. So next up, I'm going to talk a little bit about composite profile. It's a really powerful tool in the GD&T toolbox. It allows you to have a large variation in your location and still control a surface's flatness or parallelism to a very fine degree. So let me show you what I mean. So let's say we've got a really long part, right? So we got a hole on this end, hole on this end. Again, all the details on this part aren't shown. I use this as an example to talk about multiple datum reference frames. It'll work just as well for this profile discussion. Datum A is the large flat surface. Datum B is this surface here. datum C is here, and we're going to establish a datum D on this side of the part. Now, we're going to use a basic dimension here. Say it's 48 inches, okay? So we're going from datum C to datum D, the overall length of the part. The idea is we would want to have a position for this hole to A, B, and C, and the position for this hole to A, B, and D to make it slightly easier to inspect and functional enough. Okay, our first option, profile to A, B, C, that will establish D just fine. But measuring a profile of 10 thousandths from 48 inches away could be difficult, right? We might want to open up that tolerance to make it easier to inspect. This is the most restrictive we can be, a single profile to our datum reference frame. So why don't we try this? We'll just make it bigger, right? We'll make it a quarter or 3/4 of an inch. That would certainly be easier to measure, but now this surface could be so rough we might not get a good measurement to this hole, right? That wouldn't be super good. So what we want to do is, right, so that's what we would get with that 0.75, get a very, very rough surface. So what we want to do is allow that surface to be over here, wherever, but keep it relatively, straight so we can measure from it. So the way we're going to do that, we're going to leave this, but now we're just going to measure the flatness of that surface, right? So we've got this 3/4 inch, let's flatten it up. What I've done is made this a composite profile. So one geometric characteristic symbol with more than one segment. Now, in this particular example, 2 single segments means the same thing, but I'll make it composite just to show you the one symbol. Okay, so this 10 thousandths indicates that this surface needs to be flat within 10 thousandths, and it also has to adhere to this upper segment. So what that's going to do to us is flatten that surface up, but it's still free to tilt and move around within this 3/4 inches, and not exactly what we're looking for there. Now, if we wanted to make this surface perpendicular to B, which is kind of what we want, we would have to do datum B right here first. But with a composite profile or position, we cannot go out of the order of the top datums, okay? We have to stick with those. So if this is A, B, and C, we have to start with A and then go to B down here. So I'm going to do that. We're going to add datum A. Now it's difficult to see here, because datum A is that large surface, but you could potentially, without referencing datum A in the second segment, even the thin portion of the part could be out by 3/4 of an inch, which isn't what we want. So I'm going to skip ahead to datum B here. What that's going to do is snap this into shape. So now we got to be flat to 10 thousandths. We've got to be perpendicular to datum A, which is the largest surface, and perpendicular to datum B. So what that does for us is control the perpendicularity of this surface to A and B, the flatness, but it can still float within this 0.75, which, in my opinion, for the limited function of this part, is a success. Okay, so that's what composite profile can do. Now, normally composite profile is applied to more than one feature, so a pattern of features, but it can easily be applied to a single feature to give the designer more control. Now, another thing I want you to take from this is that when you see a complicated feature control frame, it often means that you have more tolerance because the designer went through a little bit of trouble to figure out where to get some extra tolerance from. It's the easiest thing in the world to slap a profile of 10 thousandths to A, B, and C, or your primary, secondary, and tertiary datums on your part onto a drawing and is normally good enough. But if you have this, it meant the designer went out of their way to find some tolerance. Now, as far as inspection goes, it's two separate checks, right? So the 0.75 to A, B, and C, and then you essentially check in the perpendicularity to 10 thousandths to A and B, but you don't have to reference C. So you don't have to go back over here for the measurement on the second segment. Now, if you measure from A, B, and C, and the surface is good to less than 10 thousandths, you only have to do a single check, all right? So if you check the bottom tolerance to the top datum references and it's good, then you're done, okay? I know it sounds a little weird, but that's essentially how it works. And if I didn't mention it before, the difference between the composite and the two single segments is essentially nothing in this case. With the two single segments, you can have the datums in a different order if you needed that for some reason, whereas the composite, they need to be in the same order and the same material condition. So if it's a different material condition, it's a different datum reference frame because you're calling out the datum in a different way. So that's it for this video, just an overview of profile and some of the applications. If you enjoyed the video, please like and subscribe. Check out the channel for more GD&T content.